everybody, I'm Vanessa Cruz, and today I'm going to teach about calculus. But please don't run away screaming, because I promise you it's not that scary. So we've all heard about integrals before, especially when we talk about area under the curve. But today we're going to talk about a special type of integrals called improper integrals.
So what kind of problems require improper integrals? There are three cases. The first case is where one of the bounds goes to infinity. In this case, it can be either positive or negative, and you'll have to set up an improper integral to be a placeholder for that infinite bound. The second case, however, is where both of the endpoints go to an undefinable number, negative infinity to positive infinity. In this case, you'll have to insert a and b as placeholders for these infinite bounds and pick a nice number in between for the separate integrals. Finally, the third case is where there is a discontinuity within the integral. In this case, you'll have to insert a placeholder for this discontinuity, and then create an improper integral with b as a placeholder.
For any of these cases, it's impossible to do a regular integral, so instead you must take the limit of the integral as a certain placeholder variable approaches infinity.
To give an example of an improper integral with infinite bounds, we have a problem where the bounds go from negative infinity to positive infinity. So to set it up, it's the integral from negative infinity to infinity of e to the x dx. So we choose a good value in between. So for here, we'll choose 0. So the limit as a approaches negative infinity of the integral of a to 0 of e to x dx plus the limit as b approaches positive infinity of the integral of 0 to b e to the x dx. And then you'll continue solving.
So sometimes you have complex integrals that are just too difficult to solve out in any normal way. So instead we must use a technique called the comparison test, which uses a simpler function that you can solve out in an easier manner to prove the convergence or divergence of the gross function that you have.
And now we have the comparison technique. To begin, we have the theorem. The theorem is that if you let f be a continuous function defined on the interval from a to infinity, such that f of x is greater than or equal to 0 for all x on the interval from a to infinity. Suppose that there is another function g, such that f of x is less than or equal to g of x, and such that ellipsis the integral from a to infinity g of x dx converges. Then we also know that the integral from a to infinity f of x dx converges. And moreover, the integral from a to infinity f of x dx is less than or equal to the integral from a to infinity g of x dx. If trying to prove a function's convergence, you must pick a function that has similar behavior but is greater and will always converge. This will push the original function down into convergence. Similarly, to prove a function's divergence, you must pick a comparable function with similar behavior but that is less than the original function and will always diverge. This will push the original function up into divergence. So how do you explain this in people words? The comparison test is essentially used to prove that picking a comparable function will push the original function either into convergence or divergence. The hardest part is picking the comparable function, so there's a couple rules and tricks that will help you. So how do you pick a comparable function? This can be quite a daunting task, so here's a few things to keep in mind. Knowing the behavior of the original function is the most important part, especially as it approaches the divergent or discontinuous portion of the function. The two main rules and tricks to keep in mind is whether or not, first, does the numerator contain either sine or cosine, because we know that those values fluctuate on the interval from -1 to 1, so the max value that they could ever reach is 1. And second is whether or not is how fast the numerator or the denominator becomes larger, so in turn how fast the function becomes smaller and approaches 0. With the first rule, where sine or cosine exists in the numerator. We know that because sine and cosine fluctuate back and forth on the interval from -1 to 1, the max value that they will ever reach is 1. So when choosing a comparable function, we can simply replace the sine x factor with 1 and create the now comparable function of 1 over x squared. So because that is so much easier to integrate, we can then substitute that back into the original integral and simply perform the integration process with that, and then continue with the improper integral process, but using a much simpler function, and then evaluating, using the comparison rules that we discussed earlier, whether or not that original function actually converges or if it diverges. So you see here that we are simply continuing the integration process. And here we took the integral and are ready to perform the next step, which is performing the FTC from 1 to b. This is how improper integrals work, by taking that substitute value and simply continuing to perform the process, just with that letter inserted, so that we can then evaluate the limit to find the estimate value that it would approach if it were an actual value and not an undefinable boundary. Right here, we know that -1 over b will go to 0 because the denominator becomes infinitely large, and anything over infinity will eventually approach 0. Therefore, we can determine, because that piece becomes 0, the only thing left is 1, so the limit of that function is then 1. So therefore, we know that 1 over x squared converges, and in turn, the original function also converges. The second rule is that we must keep in mind how quickly the denominator approaches 0. It's good to find something that's easier to integrate, like e to the x, or if you have x, you can take it down to x, or if you have x squared, you can take it down to x, because we still know that it approaches in a similar fashion. So in this case, we'll substitute 1 over x plus e to the x with 1 over e to the x, which can also be written as e to the negative x. In this problem, we'll continue with the integration process by creating an improper integral with the limit as b approaches infinity with the rest of the integral. But by substituting that comparable function, it will be much easier to integrate and perform the FTC. You can see here that we've started to perform the FTC from the first boundary of b, and then minus the second portion to 3. When evaluated as a limit, we can see that the first part, -1 over e to the b, will approach 0. And then the second portion, e to the -3, is actually a constant. So because the first portion will go to 0, it will effectively cancel out, leaving just the constant, which becomes a limit, and because it is a finite number, we know that 1 over e to the -x converges. Therefore, we also know that 1 over x plus e to the x, which is the original function, also converges.
So you may think that you might not ever use these strategies again unless you're going into the math or science field, which might be true, but there are real-world applications for this. Like, certain companies use these things to test the probability of certain events happening as time goes on infinitely. And that's all the time we have for today. We hope you learned something about improper integrals. Thanks for watching and good luck. Mr. Williams, I'll see you on Tuesday. Can't talk ever! This is the worst thing I've ever done. Okay.
Worse than Donner Party? Let's go back and watch it.
No.
And the bacon.
Can you still roll it?
She's like,
try. Practice
just
run.
roll, like.
Oh jeez.
And then yeah, you have to like
If you had that like one big burst, that kind of worked.
Okay. So we've all talked. Oh wow. Okay. So we've talked about. Okay. For any of these cases, oh wow. I have to take the limit. See?
Cue cards.
Because I suck.
Sure, Paula.
Dude, I'm freaking bad.
Johnson, D-A-W-S-O-N.
Nothing. Ooh, super shaky.
Wow.
I almost dropped it, so
7845.
shaking him is better than dropping it.
That's
True.
true. I think that you might not use this ever again.
Which you won't.
Which you won't. I know, girls. Thanks for watching. Good luck. Mr. Williams, I'll see you on Tuesday.